Good afternoon, everyone. My name is Xiang Li. I'm come from Louisiana Tech University. Today, I'm going to present a microfluidic nanostructured fluorescence sensor for biomolecular bonding detection. Here is our outline. First, I'm going to talk about the background, and then I'm going to talk about aluminum oxide nanostructure-based sensors fabrication. After that, is experiments, procedure, and results. The summary comes at last. First, let's talk about the fluorescent immunoassay. Due to its high sensitivity and multiplexing capability, the fluorescent immunoassay is one of the most widely utilized techniques in protein detection. For example, the protein microarray technology, the enzyme-linked immunoglobulin assay, they both use fluorescence detection as their main detection methods. The right side picture is a fluorescence image of an antibody microarray. However, it's still very important to improve the sensitivity of fluorescence detection, because with high sensitivity, we can increase the possibility of disease diagnosis in early stage. Also, we can reduce the expensive biological sample consumption. Usually, there are three kind of methods for fluorescence enhancement. The first method is through fluorimeter design and optimization, for example, the quantum dot development. The second type is through detection methods and apparatus improvement, for example, through improved the photo detector. The third type is advanced fluorescence enhanced substrate. So, for example, the substrate with gold nanoparticle or nanostructure. For the third method, there are two approaches. The first approach is called metallic nanomaterial substrate. Usually, the substrate is covered with gold, silver, and aluminum nanoparticle or nanostructures. The main mechanism is due to localized surface plasma resonance effects. The enhanced factor usually is up 10 to 100 times. Due to control effects, usually there are some need a dielectric material to be the fluorescent dye and metals. Sometimes the fabrication is very expensive. The other type of approach is called non-metallic nanomaterial substrate. For example, zinc oxide nanostructure, zinc oxide silicon, cautious nanostropes, tin oxide nanostructure, and anodized aluminum oxide nanostructure, which is from our group. We call it AO. The right side is a fluorescent image of rhodamine 63 on AO array. So how can we make this AO array? First, let's talk about the traditional AO fabrication. The traditional AO fabrication is usually come from a high purity aluminum oil sheet using either by one-step or two-step anodization. This process is incompatible with the standard lithography-based micro or nano fabrication process. So it's very challenging to fabricate large-scale array AO nanostructure for high-throughput application. To overcome this problem, our group developed a method to fabricate the AO arrays. We begin with the ITO on glass with rigorous cleaning. Then we're using different process to fabricate aluminum pattern on this substrate. After that, we apply one-step anodization process. Finally, the AO array is formed, and a PDM's microfluidic chip can be bound to the substrate to form a microfluidic system. Let's see the fabricated device. Okay, so here is a fluorescence device. Let's see the 3D sketch first. We can see there are three fluorescent AO sensors on this glass substrate. The pattern is either being micro-light pattern or micro-circle pattern. And there is a PDMS chip on the substrate. And here is a photo of the fabricated device. We can see that in the middle there are three dark dots. That's our AO sensor. And here we show a SEM image of the nanostructure on the AO sensor. You can see there are numerous nanopore distributed on the surface. The pore size is about 10 to 20 nanometers. So let's see the model we use and the experiment procedure. We employ the binding between protein A and IgG as a simple model. It is why use the simple model for immunoassay. Basically, the protein A will capture IgG in biosample solution. And the C block is used to prevent the non-specific bonding between IgG and the substrate. And here is the procedure. First, we flow protein A to PDM chambers, and let the protein A stay for certain times to enable it to immobilize on the surface. Then we flow PBS to watch unbonded protein A. After that, we flow C block and they stay for a certain time to occupy the space between protein A biomoleculars. And we flow PBS solution again to watch unbonded C block. After that, the IgG biosample solution is flowed through and stay for a certain time to allow the protein A capture the IgG as many as possible. After that, PBS solution is flowed again to watch the unbonded IgG. So let's see some results. Here is a fluorescent image on AO sensor after biomolecular binding. The left side is a bright field image, and right side is a fluorescent image. By looking at the fluorescent image, we can see the AO emission very strong fluorescent signal by compared to the glass. We know although the biomolecular bonding already happened in the whole area, including the glass and AO. So this experiment shows the AO's capability of enhanced fluorescence signal. And here is another group of fluorescent image. It is on circular pattern-based sensor. In this test, we use 3 different concentration of IgG from 13.3 nanomole to 1.33 micromole. The first row is a bright field image, and the second row is fluorescent image. The third row is fluorescent intensity plot along a horizontal line in the middle of the fig B. The background of the bare AAO or bare glass has been subjected in this fluorescent intensity plot. By examining the fluorescent intensity plot in the row C, we can see in the most right fluorescent intensity plot, we still can see some very weak fluorescence come from the glass. But at least two concentrations, there are just the acknowledgeable fluorescent signal come from the glass. While compared to all 3 AO, we can see there are very clear fluorescent signal from the AO. This measurement indicates our AO can detect a IgG-L concentration of 30.3 nanomole without any device optimization under a traditional fluorescence microscope. Here we show another image of fluorescence image. This time it's microlight-based sensor. The concentration is 0.1 nanogram per square millimeter. The figure A is a bright field image. In this experiment, the biomolecular bonding is only happened in the upper area. So you can see there is a very light boundary in the middle of the picture. The second image is the fluorescent image, and the third image is the fluorescent intensity plot along a horizontal line in the fig B. Again, this time the background of bare AO or bare glass has been subjected. By looking the fig C fluorescent intensity plot, we can definitely differentiate the AAO and the glass at this concentration at 0.1 nanogram per square millimeter. Also, our group fabricated some reconfigurable sample delivery system which can automatically generate different biological sample concentration. So here is a 3D sketch. In this system, there are 3 inlets. The 3 inlets is for biological sample and also for diluting solution. And between the inlet and the AO array sensor, there are several serpentine microchannels which is used to generate different concentration of biological sample. Here is a fabricated device. We can, in this device, we have 5-row AO array sensors. Here we show a fluorescent image of protein A binding with IgG. This time the IgG is labeled by rhodamine. And each image is corresponding to each row on this device. So in this test, the system generates a symmetrical concentration profile of IgG concentration. So this means we have a highest concentration in the middle, and the concentration decrease along two sides, and the symmetrical side have the same concentration. And here we show another result of different concentration profile. This time the protein A is binding with IgG, and the IgG is labeled by FITC. And this time the system produces a symmetrical concentration profile, which means the IgG have the highest concentration in the left, and the concentration will decrease on the right. We also apply our AO on cell imaging. We use each cell labeled with FITC conjugate con A. And on the left side, the yeast is on glass. Right side, the yeast is on AO substrate. The top row is a bright field image, and the second row is a fluorescence image. By comparing the fluorescent image, we can see the yeast on AO substrates show a very stronger fluorescence intensity than on glass. These tests indicate the AO's application in cellular imaging. So there are two possible mechanisms for the enhancement. The first is called surface scattering effect of the AO film. The redistribution of electromagnetic field with surface intensity will eventually result in enhanced fluorescence. The second possible mechanism we think is waving guiding property of nanoscale grains in the AO film. It is similar to zinc oxide nanorobe to guide visible light effectively, thereby enhancing the intensity of evanescence field. Our AO nanostructure also can serve as efficient evanescence waveguide, and eventually will enable fluorescent enhancement tremendously. Here's summary. So we fabricate AO micropatterned arrays. And the AO micropatterned array-based fluorescence sensor has been tested. And experiments show this type of sensor can detect IgG concentration at 30.3 nanomole by using a traditional fluorescence microscope. This technology offers great potential for multiplex fluorescent-based biosensing or cell imaging. Thank you for listening.